I will leave you to relax after tomorrow. So
Speaking
tomorrow
of
will
which,
be a
I'm
lot.
sure Baka should be here as well.
Bakkar is having fun these days. That's fine. All right.
I'll deal
Let
with
me
him.
let
I'll
me.
deal with him on the 14th.
In fact, let me ruin his fun for a moment. Let me ask his father to send him.
It won't work because from what I hear, his father works late into the night, and from what Abu Bakr has been telling me, he's been sleeping at this time
Yes,
for the
I know.
past 2 weeks.
He's a clever person. That's fine. Anyway, so last time we basically started with mainly how the stars are, what they do. So today we are gonna look at the cosmology part. First of all, in cosmology, we are gonna learn about the emission spectra. We have already done that in the quantum physics, but just to quickly revise this and how it applies here. So what you guys need to remember is that elements in a star are usually hydrogen, helium, and other gases. Okay, so generally what you see in stars is that there will be a spectrum, like what you receive from them is a black spectrum with certain very specific discrete colored lines. For example, you would be receiving a lot of lines like these, and then maybe some lines like these, lines like these, maybe some orange ones, and maybe a bit reddish ones as well. Depends on the type of gases it has. Obviously, that this is, let's suppose this the emission, this is basically the regular hydrogen. Sorry, did I record this? Okay, yeah. Regular hydrogen uh, emission spectra in the lab. So that's this. Okay. Now, what we want is, when we look at any star, we see that the hydrogen spectra seems like a bit shifted. So this line would be somewhere here, like this. It would be less blue, a bit more, less green, less orange, sorry, more orange, and more red. Now, this shift that you see right now, this shift like this is observed through the stars spectra. And what we notice is that it is sort of shifted hydrogen spectra measured from a distant galaxy. Now, obviously, if you look at this side, these are the blue wavelengths, and this side are more red wavelengths, which means that they have higher wavelengths. So these lines seem to be shifted towards red. Now, a lot of people write they shifted. A lot of people write they become red, which is a wrong way to say. They're just shifted towards red. All of them do not become red. So remember that. Now, this thing that you see, witness, is because that when astronomers observe light from distant galaxies, they observe differences in the spectral lines to the light from the sun. Due to the same characteristic pattern, elements can be easily identified, because in quantum physics we have learned that each element has a unique pattern because of the energy levels inside, right? However, it seems slightly sorry, it seems slightly shifted. Okay. Now, you guys need to remember lines in the spectra from distant galaxies show increase in wavelength. One. Number two, lines are moved or shifted towards red end of the spectrum. So these are the keywords that you need to be aware of. Now the question is why this is happening? Because of Doppler's redshift. We've already done that in AS, but it was largely according to sound. But this time we're going to look at according to light. So Doppler's redshift is the apparent change in wavelength or frequency of the radiation from a source. In fact, let's write this Doppler shift first, and then we'll define each one differently. So, from a source due to its relative motion from the observer. So the keywords in this one are apparent change and relative motion. Now, obviously, we have two kinds of shifts. You have red shift and you have blue shift. Now, in red shift, we can say that basically it happens when object is moving away from Earth. And if the object is moving towards Earth, then we can say it is blue shift. Now, just to give you an insight of this, shift is prominent when the relative speed is notable. And shift is observed by spectra of distant galaxies, like that. So you can write it down, please.
Done.
Okay. Okay. Now, kids, going to the next. If you guys have any questions in this, please let me know. Now, specifically, they will ask you about the definition of redshift. This will be a 2-mark definition. And if it comes, then what you're going to do is write that it is the fractional increase in wavelength due to the source and observer receding. Receding means moving away, okay, from each other. Now, the formula to find this is very simple. Change in lambda over lambda is equal to change in frequency over frequency equals to V upon C. Let me explain each and everything in this. So change in lambda, change in wavelength. This is the wavelength emitted from source. This, kids, is the change in frequency. This would be frequency emitted from source. This would be the speed of recession, and that would be the speed of light. Speed of recession means that at which speed it is moving away from us. So please write this down.
Done.
Okay. Now, one thing that you guys need to remember about this equation, please write a note, that this equation only works for non-relativistic galaxies. Now, what this word means, non-relativistic, a body moving at a speed much lower than speed of light. All right, so this is for this, and which is case of almost everybody. Okay. Now, keeping up with that, then let's have a look at the at a question. Okay. So let's write it down. It says a particle sorry, a particular line, sorry, a particular line, particular. Sometimes, I can't even understand my own writing. Okay. In the spectrum of light, from a source in the lab has a frequency of 4.570 into 10 raised to 14 hertz. The same line in the spectrum of light from a distant galaxy has a frequency of 4.547 into 10 raised to 14 hertz. Now, what speed is the distant galaxy moving in relation to Earth. Comment if it is moving away or towards the Earth. So first off, we're going to look at this. So we're going to use this. Change in frequency will be 4 point.
Considering the frequency is less, doesn't mean it's a redshift.
Yeah, it has been redshifting. That's good. You can look at it from the values itself. So that's right. So use this, and then we want to find the speed of recession and the speed of light, like that. You should be getting 1.5 into 10 raised to 6 meters per second recession. And we would be writing that obviously the observed frequency is less than the frequency of source. So the source is receding, which basically means moving away, just like that. So it's pretty simple, this chapter, with the formulas as well. So you can remember that.
So anything else?
Yeah, no, we have a lot of things. We have Hubble's law still left, and the last part of this. So we're gonna do that. So you can write it down, please. Okay. Now, just wanna again write down a common mistake. A common mistake is that a lot of people say there is a right answer. Whenever they ask you redshift, you say redshift means wavelength of spectral lines increases towards now the red end of spectrum. This is the right way to write. The wrong way, a lot of people write this, just save time. This is wrong. Do not write becomes red. Now, if you write that, obviously you're wrong, because obviously the lines do not become red; they just slightly, shift. That's why.
Can't we just say wavelength increases closer to wavelength of red light?
Mm, like, you can say that, but you can't say it becomes red. You can't say that, right? Because it doesn't become red. It just becomes closer to it. That's right. Okay. Now, why are we studying redshift? What is the use of this in today's world? And the biggest thing that we need to basically focus on is it is an evidence of an expanding universe. So let's write that. Redshift shows the evidence of expanding universe by observation of many galaxies. We have learned that the faster the galaxy is moving away from us, the more red shifted the light from it is observed. Right, kids? That's something important. So why it is happening? Because we can basically see it from the balloon analogy. Okay, let me make a nice person. Okay, so let's copy this person. Now suppose you get a balloon with those fancy, polka dots on it. So there are 4 dots. And you fill in more air, so the balloon becomes bigger in size. So what happens is that this balloon now, these polka dots will go away from each other more. So this is just like, you know, will be like expanded from each other or moved away from each other like this. So this is how sort of, the galaxy is kind of expanding. All right, kids. Now, one of the biggest scientific discoveries were made by few, were made by the scientist called Hubble. And he has basically observed so many galaxies in his lifetime that today we use his method to do the same. And even in our in the space near Earth, we have a Hubble's telescope as well that observes distant galaxies today still. So this guy, his name is, by the way, Edwin Hubble. So let's credit him. Edwin Hubble. Uh-oh. Observed many galaxies using the data gathered by redshift and standard candles methodology. All right, so he used stand candles for distances, redshift for speed. Now, you guys should understand that redshift enabled him to find velocity of recession, and standard candles enabled him to find the distance from Earth. So that's a good thing, right? Now, speaking of Hubble's constant, he presented us with Hubble's law. And the Hubble's law is pretty simple. It says the recession oh my god, recession speed of galaxies moving away from us is proportional to their distance from Earth, which basically means that their speed, the the further away they are from us, they have a higher speed as well. Now, when you remove this proportionality sign, you got to put a Hubble constant. Hubble constant is this h naught. It is measured in second minus 1. They will give you this themselves. And the distance between galaxy and Earth is d, obviously measured in meters. And this is the velocity of precession that we have found using the redshift. It is taken in meters per second, like that. All right, kids, write it down, please.
Done.
Okay. Everybody's done. Should I go forward, please?
Yes.
Now, interestingly, he has basically developed a system. It's just a graph. In this graph, every now and then, every time we go up the cosmic ladder, I explained to you, I think, before as well, or maybe that is in IGCSC. Cosmic ladder means
No,
every
you
time.
did. You explained the cosmic ladder. Where is it? Yes, you cosmic distance ladder. Each standard method we can be used to measure distances within a certain range. Collecting data and measurements from each method allows astronauts to build a larger picture of the scale of universe, which is the cosmic distance ladder.
Yes, yes. So every time you make a discovery about a new galaxy, so they are plotted against on a graph against the speed and distance. And when you make a line of best fit, that gives you basically a graph like that. Now, one is now more distant galaxies are moving away at a higher velocity or vice versa. Like the near ones are like of less velocity. So if you find a velocity here and you find it from here as well, so you can end up getting the gradient, and this gradient of this line basically gives you the Hubble constant, like that. So you guys need to remember that. Okay, kids. Interestingly, this Hubble constant keeps on changing every now and then, because as new discoveries are made, so the line shifts a bit up or down, but generally it has the same uh, gradient, just a little bit shift. We're gonna compare it with last year when I taught. wrote the notes. So let's see what happens today. But anyway, why this is so important? Because again, using this Hubble's constant, we can actually gather the information about the age of universe, then when it was, when it came into existence. So if the galaxies are moving away from each other, that means they must have started from same point at same time in the past. All right, kids. This also means if it is considered to be true, the universe likely began in an extremely hot and dense singular point, which subsequently began to expand very quickly. Now, this idea, you might have heard this before as well. This whole thing is related to obviously the Big Bang. It doesn't look nice. Let me just move it here. Okay. So if you watch this show called The Big Bang Theory, this show has this song, initial, the starting one, that 14 billion years ago, our universe was hot and then started from one point, right? Like that. So you can watch that show as well. It's quite, a good laugh for some time. And there are a lot of physics, puns in that. All right. So this idea is basically known as the Big Bang Theory. And if we extrapolate Hubble's law, back to the point where it believed universe started, its expansion, the age of universe can be found using a simple formula. The age of universe is 1 upon Hubble constant. So this, my friends, is the age of universe, and this is Hubble constant. Now today we can also find that. We're just 5 minutes. Just write it down quickly so we can find the age of universe, and then we will be done.
Done.
Okay, give me 1 second, please. Okay, now that's pretty good. Now let's find the age of universe using our best friend Google. So first, time to write the question. Oh, what is this? What exactly is happening here? Okay,
13.7 billion years, give or take 200.
give or take 200 billion years. Okay,
No, 200 years.
okay, let's see.
That's actually pretty accurate.
You will find it. A galaxy is moving away with a speed of 2.1 times 10 raised to 7 meters per second. The galaxy is at a distance of 9.5 times 10 raised to 24 meters from Earth. Assuming the speed remains constant, what is the age of universe? Can you do that, please? So obviously in this question, you guys need to find the Hubble constant first using the law, and then from that, the age of universe using 1 upon Hubble constant. Let's see if you guys can do that. Interesting.
Four point five two times 10 to the power 17.
No, wrong. Very bad. Oh, 4.52. That is seconds. You need to find it in years.
All right, then first divide this by 60 to get it in minutes, divide by 60 again in hours, divide this by 24 in days, then divide by 365. You get approximately 1.43 times 10 to the power 10.
1.43 times. Okay, so that would be 14.3 billion years.
Which is in line.
With your estimate, little bit in line. Yeah, it's good. So you should get 2.2 into 10 is to minus 18 second minus 1. This is Hubble constant, and then for age of universe, you guys need to divide this. That would come as 4.52 times 10 raised to 17 seconds, and then in order to convert it into basically years, you need to divide this whole thing with 365 days, 24 hours, 60 minutes, and 60 seconds. That would give you 1.43 times 10 raised to 10 years. So billion is 10 raised to 9, by the way, if you don't know. So which means 14.3 billion years ago, on an estimate, the universe was formed. All right, kids, do you understand that? like that.
Yes. Sir.
So this is the end of our syllabus. Yay! I thought we'd take another class tomorrow, but it's okay. It's good that you guys did it. So we're done with A2, and now a very small thing before you go. Okay. So the crash course will start from first week. Obviously, they will tell you, the academy people, what are the timings for that. So I'm going to create a new class for you. You can basically join in, and there is something very important before you come to the class. Okay, so let me just create a class and then I'll tell you.
All right,
So
sir. And thank you so much for your
so
effort.
this is A2 crash. Wait a second, 2024. Okay, now so kids, I just need you to join the group, and then I'm sharing you a book. Okay, this is a workbook that I made. It is essential for you to print it out if you do it like with a pen. Otherwise, you can also use it uh, with normal digital work if you want to do that. It's up to you. So I'm sending it just now. Right here. Okay. So here you go. And the book is like, let me just attach that file. It's I created these books. It will just download. So it will be uploaded in a bit in the group. Just download this book, and then you need to print it out before you come to the crash. Okay, it's very important. All right, kids. Do you understand? Any questions now? All right. So I will see you then. Have a nice day. Bye.
Thank you, Allah Hafiz.
Allah Hafiz.
Thank you.
Bye.